Okay, so in lecture 18, we're going to learn the last basic proof rule of the entire semester. This is the proof rule of existential elimination. And naturally enough, existential elimination is the most complicated proof rule that you'll learn the entire semester. In many ways, it's like the rule of disjunction elimination. However, although it's not as syntactically complicated, that is, it's the calculation of dependency numbers is not as complicated. Conceptually, it's even slightly more difficult than disjunction elimination. So the fact is, the name existential elimination is a bit misleading, as was the name disjunction elimination, because the truth is, you cannot directly eliminate a disjunction, right? From a disjunction, say P or Q, you can't eliminate the disjunction. You can't say from P or Q, I infer P, or from P or Q, I infer Q. That's not valid. So in truth, disjunction elimination is a way of arguing from a disjunction so that the final result doesn't involve necessarily a disjunction. So you'll remember from the case of disjunction elimination, the argument style was proof by cases. So in other words, you argue from each disjunct separately. If you can arrive at the same conclusion in both cases, then the disjunction itself implies that conclusion. The idea is the same with existential elimination. So here's the idea. If you have an existential premise, a premise that says there is something with some feature. Now, how can you can't eliminate that. You can't just say, therefore, Bob has that feature, or therefore, Sally has that feature. You can't infer from an existential to an instance. So like disjunction elimination, it's going to be from the existential, you argue from each disjunct to the same conclusion. From an existential, in this case, you argue from the instance of that existential statement with an arbitrary name to a conclusion. And if that conclusion doesn't involve the name, that conclusion follows from the existential sentence itself. Okay. Again, as so often happens, the abstract statement of the rule, much more difficult than concrete instances of applying the rule. Okay, so let's actually look at a very simple case where we're going to need to use existential elimination in order to derive something that should be obviously valid. So from the premise, there is something that's F and G. How can we arrive at the conclusion there is something that's F? Okay, so what I'll do is I'll just give you the proof, and then I'll explain how the rule was used in the proof. So the assumption there is something that's F and G. Okay, now, as I just said, you can't argue from this premise, 1, 2, A is F and G, or B is F and G. That's not valid. What I'm going to do is I'm going to assume on the next line that A is F and G. So what this is on line 2 is it's an instance of the existential sentence that occurs on line 1. So what's actually going on here on line 2, so notice I put the new dependency number 2 to indicate it's a new assumption. What's actually going on here, though, is this mimics a pattern of reasoning where you say, let A be such a thing. So if I say there is something that's F and G, if we agree, if you and I agree, there is something that's F and G, the next move I could make is let's make up a name A for one of those things that is F and G. We don't know which one, but you told me we agreed there is something that's F and G, so let that thing be called A. So in truth, the assumption here on line 2, it just says it says A is F and A is G, but in the background, the idea is let A be the thing that is assumed to exist that is F and G. Let it be one of those things. Now I'll argue to the conclusion that I believe follows from the existential sentence on line 1. So I'm going to take out just the F from line 2. So conjunction elimination. And now there is something that's F. So from line 3, existential introduction. Okay, so this is clear from line 2, which says A is F and A is G. It follows that something's F. That's clear. That's not problematic. What's interesting and where the new rule comes into play is, look what happened. On line 4, I derived a claim from line 2. Line 2 is an instance of the existential sentence. But now the final claim on line 4 doesn't involve that name A anymore. So it's something that will follow no matter what name we chose. So it's not sensitive to the choice of name we made. So in fact, it follows from line 1. That is what I just said is the rule of existential elimination. So here's how it works. On line 5 now, I repeat the conclusion that I got on line 4, but now I'm going to change and say it doesn't follow from line 2, it follows from line 1. So it goes like this. 1 is the existential statement. 2, in this case, is the instance of the existential statement. And 4 is the conclusion that does not contain the name that occurs in the instance. So in this case, the name A. So this now is existential elimination. So that is a correct application of the rule existential elimination. In truth, the rule existential elimination, the restrictions are very nitpicky. So I already named the first restriction. The first restriction is that name that occurs in the instance. So go back and I'll highlight it here. So this name, A, that occurs in the instance cannot occur down here in the conclusion that you're going to eliminate, that you're going to draw from the existential sentence, that conclusion. That's one restriction. Another restriction is actually that name A can't occur in the dependencies of the existential statement back here. So it can't occur in these dependencies. It actually also can't occur in the dependencies of the statement on line 4, except for that name itself, except for the instance itself that occurs on line 2. Okay, all of those nitpicky rules about A not occurring here and A not occurring there, the idea is to enforce that A is an arbitrary name. It's not a name of somebody you already know something about. It was a name you picked out new as an instance of the existential sentence for reasoning purposes. So the nitpicky rules about A doesn't occur here, A doesn't occur there, there's one way you can always avoid violating those rules is you just pick a new name A for the instance and then reason for it, as we've done in this case. Okay, so let's just look at a slightly different kind of example now of the rule existential elimination. So here we start with the universal premise. Anything, if it's F, then P. So for anything, if it is F, then P, that's just our assumption. And now we're going to argue for the conclusion. If something is F, then P. Now the conclusion is not an existential statement. The conclusion is a conditional. So as so often with conditional statements, I'll just argue by assuming the premise, there is something that's F, and then I'll try to derive the conclusion, P. Okay, now I'll use existential elimination. So here's the idea, is now I'm going to pick an instance of that existential claim, the existential claim on line 2, something is F. I pick an instance A and I say A is F, but that's a new assumption. I don't derive that from line 2. I assume A is something that makes that existential sentence true. So that's a new assumption. But now I'm going to reason for my conclusion, which in this case is P. I'm going to try to get P. Okay, but now on line 1, I have anything, if it is F, if that thing is F, then P. So I can instantiate 1 to the name A. So it is true in particular of A that if it is F, then P. So that's from 1 universal elimination. And so now modus ponens from 4 and 3 will give me P. Okay. Now notice though, here P on line 5 depends on line 3. Okay, so now I want to apply existential elimination to change that dependency on line 3 to a dependency on line 2. So here I go now from assert P again, but now I'm going to say this follows from 1, 2, because I derived from 2, 3, 5 existential elimination. Okay, so the P on line 5, it follows from the instance on line 3 of the existential. So therefore it follows from the existential because it doesn't contain, P does not contain the name A, and we didn't use anything else that contained the name A. So none of the dependencies that came in except for this particular instance here, none of the dependencies brought in facts about A from the outside. So therefore from 1 and 2, we get P. So now finally, we can discharge the antecedent of the conditional. So I can write exist X, fx arrow P. So now 2, 6, conditional proof. So just from line 1, there's something such that if it's F, then P. Okay. Okay. Here's a slightly, it looks very similar to the one we just did, but it's actually different in structure. Okay, this says from the premise, there is something such that if it's F, then P, we can derive that everything, if everything is F, then P. Okay, again, the conclusion is a conditional, so I'll assume the antecedent, everything is F. Okay, now you should be probably getting used to this game at this point. We'll see, okay, I have an instance on line, or sorry, on line 1, I have an existential. Now I'm gonna write an instance of that existential. If FA, then P. This is a new assumption. It doesn't follow from line 1. I'm using the assumption on line 3 to argue about what is true for any case of the existential on line 1. Okay, now I can invoke line 2, which says everything is F. So A is F. Okay, at this stage now, I've argued from the instance on line 3 to P, but if I want at this stage now, I can realize it doesn't, that argument from the instance on line 3 to 5 doesn't depend on anything involved in the name A. And so I can now just go to P again, in this case now from 1 and 2. So this is 1, the instance 3, and then the conclusion 5, existential elimination. Okay, so then finally, if everything is F, then P. So 2, 6, conditional proof. Okay, so on to the last example from this session, and that's a tautology. So this, what we're going to show now is this claim. The claim is there is something such that if it's F, then everything is F. Okay, and I really like this particular problem because this particular proof, because it's actually very counterintuitive. So if you think about it, it says something, this is true no matter what F is. It's just a tautology, a truth of logic. So it's always true, this claims for any F, there's something that if it's F, then everyone is F, then everything is F. Okay, so think about it, say, for example, in relation to our class. There's somebody in the class, there's somebody such that if that person gets an A, then everyone in the class gets an A. That's a pretty surprising fact, but it's true according to logic. Okay, so how do we prove this? Now, this proof will not yield to direct attack. So you're not going to find an instance. You're not going to find the special name A, the thing such that if it's F, then everything is F. So we're going to have to argue in a slightly less direct way. Okay, so I'm going to assume the negation of this claim, and I'm going to derive a contradiction. Okay. Now, actually, I have done this proof and proofs like this so many times that what I remember negative paradox. And so what I see very quickly when I look at this is I see if little a were not F, then it would be true that if little a is F, then everything is F. So that's just negative paradox. So in other words, if I assume on line 2 that little a is not F, I'm going to end up with a contradiction to line 1. Okay, so it's going to follow from line 1. For any name A, it will follow that A is F. Okay, now what that's going to give me then is everything is F, and that's going to again give me a contradiction to line 1. So what I'm going to do is I'm going to use line 1 I'm going to get a contradiction that leads to for all y, Fy. I'm going to get for all y, Fy from the negation of line 1, but then I'm going to show that contradicts line 1. Okay, so this is a new assumption on line 2. Now I'm going to allow myself to use negative paradox again. So Fa, if Fa, then for all y, Fy. So that's just 2 cutting in negative paradox. Okay, so then there is something such that if it is F, then everything is F. That's a direct contradiction against line 1. So that's just 2 existential introduction. So now I'm going to do a reductio. So I get something such that if it's F, then everything is F. And from line 1, it's not true that there's something such that if it's F, then everything is F. So 4, 1 and introduction. 1, 2. Okay, so now not Fa. So that's 2 to 5. Reductio ad absurdum. 1. Okay, so now I'm into the second phase of my proof strategy. So now I've got the negation of the conclusion I want, which I just want to show a contradiction follows from that negation. I've got now that Fa follows, but the name A doesn't occur in 1, so I can universalize this Fa. I can now infer that everything is F. So for all y, Fy. So 7, universal introduction. Okay, now I'm going to use positive paradox and say, if B is F, and I'm just using B because I don't want to get confused with what happened before with A. So B is a choice of a new name. You're going to see I'm just drawing out a contradiction with line 1. So if B were F, then everything would be F. So that's just now 8, cutting in positive paradox. Okay, now once again, I have a contradiction with line 1, but now in this case, there's no auxiliary assumption. It's line 1 leads to line 1's the negation of line 1. So line 1 is going to be self-contradictory. So exists in X such that if Fx, then for all y, Fy. So that's 9, existential introduction. Okay, so there. Now I have a contradiction. Line 1 leads to this contradiction, which is namely line 1 and its own negation, or in this case, the absence of a negation on it. So finally, on line 12, I get not exist x, fx arrow for all y, gy. Okay, so that's 1, 11, reductio ad absurdum. And notice I just made a little typo, an all-important typo, and that is I forgot to erase the dependency number, right? So in other words, 1 leads to a contradiction on line 11, but line 11 only depends on 1. So now if you do reductio, it disappears, that dependency on 1. So it's this on line 12 follows from no premises. But now if we use double negation elimination, that is just exist x fx, if fx, then for all y. Oh my, there's on the previous line, once again, another typo. Let me go back and make this properly. It's not G, this is F. Okay, just a little slip of the hand. So now for all y, Fy. Again, no dependencies, so 12, double negation. Okay, so that's a surprising tautology. That's a not so simple proof. Using cut and negative paradox and positive paradox, we at least reduced some of the length here down to 13 lines. Okay, in summary, what we learned today, we learned the most complicated rule of proof. So we learned that from an existential, you can't derive things directly because existential doesn't tell you what thing has the feature, just says something has the feature. The strategy existential elimination says, if you have an existential and then you can argue from an instance of that existential to a conclusion, then that conclusion under certain specific conditions follows from the existential statement. Those specific conditions basically correspond to the conclusion doesn't contain the name that you arbitrarily chose as an instance of the existential, nor did you bring in any other information about that name along the way. So the only information you used was the fact that that thing was an instance of the existential statement.